Hello everyone. Today I am presenting my machine learning project focused on predicting the net hourly electrical energy output of a combined cycle power plant. This type of power plant uses both gas and steam turbines to generate electricity. Our dataset consists of over 9,500 hourly readings. Our objective is to use 4 environmental sensors: ambient temperature, exhaust vacuum, ambient pressure, and relative humidity, to accurately predict the PE, or energy output. Because we are predicting a continuous numerical value, I have identified this as a supervised learning regression task. To measure our success, I've selected mean absolute error, MAE, as my primary metric because it tells us, in plain language, exactly how many megawatts our predictions are off by on average. In determining my modeling approach, I considered 2 different algorithms. First, I used multiple linear regression as a baseline because it is simple and interpretable. Second, I chose a random forest regressor. I selected random forest because it is an ensemble method that can capture nonlinear relationships that a simple line might miss. For example, how humidity and temperature might interact differently at extreme ranges. My strategy was to compare these 2 algorithms to see which one handles the fluctuations in power plant efficiency more effectively. I used the 4 features provided in the dataset, AT, V, AP, and RH, without any initial transformations to see how the raw sensor data performed. To build a robust model, I first performed an 80-20 data split, setting aside 20% of the data, about 1,900 samples, as a holdout test set. This data was never shown to the models during training to ensure an unbiased final evaluation. For the training phase, I used a 5-fold cross-validation strategy. Instead of just testing on one small slice of data, cross-validation rotates the data 5 times, ensuring that the model performs consistently across the entire training set. During this validation phase, the linear regression model returned a root mean squared error of 4.57, while the random forest achieved a significantly better score of 3.46. Based on these validation results, I selected the random forest as my final model. Now, let's look at how the final model performed on the unseen test set. The results were excellent. The mean absolute error was 2.33 megawatts. To put that into context, the power plant's output ranges from 420 to nearly 500 megawatts. An average error of only 2.3 megawatts means our model is accurate to within about 0.5%. The R-squared score was 0.96, meaning our model explains 96% of the variance in energy output. As you can see in the scatter plot on the screen, the teal prediction points follow the red, perfect prediction line very closely, with very few outliers. Finally, to interpret the model, I analyzed feature importance. It is clear that ambient temperature, AT, and exhaust vacuum, V, are the most critical factors. This makes sense physically. As temperature rises, air density decreases, which often reduces the efficiency of gas turbines. In conclusion, by comparing a linear and a nonlinear approach and using a rigorous cross-validation strategy, I was able to build a model that can predict power plant output with high precision. This model could be used by plant operators to forecast energy production based on weather forecasts, helping to balance the power grid more effectively. Thank you for your time, and I look forward to your feedback.